Okay, hi everybody, let's start. So, first, some administrative announcements. Well, homework 1 is due right now on Gradescope, in case you forgot. And homework number 2 is online. Due next Friday. And so I want to mention that oh, by the way, please feel free to turn on your video. I'm recording. I have some other computer right now, which supposedly should work all right. So compared to homework 1, homework 2 and the next ones are going to be slightly more challenging, or maybe not slightly. Anyways, homework 1 was sort of a warm-up because we didn't learn as much new stuff in the first week. So, and the only way to kind of learn the stuff, to kind of truly understand them, these objects, is to compute with them. And so I encourage everybody to start early on homework 2, and whenever you see a new object, make a table. Just compute the first few numbers, or maybe if you're a computer scientist, you can write a program. That also helps a lot. If you just program these objects, I guarantee you're going to understand them much better. So and this week and in the next couple of weeks, we're going to apply the basic methods we learned in class to all different kinds of combinatorial objects. So there's going to be a lot of objects which are all very natural, and then we're going to count them using the principles we learned last week. So advanced counting. Which, by the way, any questions on the homeworks or any other? The syllabus does not mention exam dates. Have they been decided yet? Not yet. I'm gonna give you a 2-week notice before the midterm. There's gonna be one midterm somewhere in the middle of the quarter, and you're gonna get an email in advance. Any other questions? All right. Okay, let's do some advanced counting. So, and the first object we're going to consider is weak compositions. So, and this is a very natural object, as many of them are going to be. So, a weak composition of n, just n is some number, and then weak composition is a sequence A1, A2 up to AK, such that each AI is non-negative, and they sum up A1 plus A2 plus etc. plus AK. The sum is equal to n. All right. So, for example, I don't know, 7, 0, 0, 1, 5, 0, 6 is a weak composition of whatever the sum of these numbers is, of 19, I guess. And so the question is, how do you count them? So question that I'm going to ask is, how many weak compositions of n are there? And so first, for some of the objects we're going to consider, there is going to be a simple formula. For some of them, the formula is going to be slightly complicated. But in this case, the formula is very simple. So if anybody has any idea, you can let me know. Stars and bars. Yes, thank you. Okay, that is not only the answer to my question, but also the proof. But all right, let me try to explain stars and bars. So first of all, here is the claim. The number of weak compositions of n is given by n plus k minus 1, choose n. So it's just a single binomial coefficient. Yeah, so maybe I should try an example to convince you that the formula is correct. So maybe n, should I try n equals to 2? Yeah, so here k is the number of spots, right? So compositions, maybe I should write compositions a1, a2, all the way up to k. So maybe n equals to 2, and I don't know, k maybe 3. Should I try that? Then the weak compositions of 2 of length 3 are 2, 0, 0, 0, 2, 0, 0, 0, 2, 1, 1, 0, 1, 0, 1, 0, 1, 1. So there are 6. There are 6 of them, and then n plus k minus 1 choose n is 4 choose 2 is 6. So yeah, luckily for me this worked out, and the proof is sort of a famous argument, right? You kind of, if you are exposed to some sort of Olympiad programs or any kind of advanced combinatorics, you immediately see this argument. So it's a very useful argument to kind of it applies in several different problems. So the idea is, well, you want to interpret this binomial coefficient as, well, it counts subsets. So you need to translate subsets into compositions. And maybe I should, so because of the symmetry of binomial coefficients, n plus k minus 1, choose k minus 1. Right, so, okay, so n plus k minus 1, choose, let's say, k minus 1, counts subsets of course, bracket n plus k minus 1 of size k minus 1. K minus 1. So I want to somehow convert that object into a composition. So the idea is that you imagine n plus k minus 1 empty spots. So in the case of n equals to 2 and k equals 3, I should imagine 5 empty spots. Okay, now what my binomial coefficient is doing is telling me, so I'm gonna place yeah, let's say n balls, place n balls into these empty spots. So each empty spot can contain at most 1 ball, and so place n balls, leaving k minus 1 empty spots. Right, so maybe, yeah, let me try a bigger example. So I'm gonna maybe let's try 10 spots. And then I'm gonna place some number of balls. So I'm gonna just choose randomly and place n balls, maybe something like this. 1, 2, 3, yeah. So here, n is equal to 6. And k minus 1 is the number of empty spots. So k is equal to 5. Okay, and then I'm gonna, the next thing I'm gonna do is I'm gonna, yeah, so these balls are stars, and the empty spots are gonna be the walls. So the idea is that you place a wall at each of the k minus 1 empty spots. So here's where my walls are going to go. And then basically the way to convert this into a composition is to just record. So there's k minus 1 walls, right? So there's k places, there's k kind of spaces between the walls. So what you do is you just record the number of balls in each space between two walls. Let A1 all the way up to AK record the number of balls between each pair of walls. So I have kind of some invisible walls on the left and on the right, and then between any two walls I record the number of balls. So this particular example is going to give me what? 2, 0, 1, 0, 3. And yeah, so the claim is that this gives a bijection between subsets of n, between k minus 1 element subsets of bracket n plus k minus 1 and weak compositions of bracket n. Well, sorry, of just n. There is no bracket n here. Okay, so that's the, well, and the claim is very easy to see, right? You can, if I only show you a composition, then it tells you exactly what to do, right? You place 2 balls and then a wall, and then 0 balls and then a wall. So maybe should I try some other, maybe A1 up to AK, if it's given by 3, 0, 0, 5, 1, 2, 0. Then the corresponding sequence of walls is going to be balls, stars and bars is going to be, I put 3 balls and then a wall, then 0 balls and then a wall, then 0 balls and then a wall, then 5 balls, a wall, 1 ball, a wall, 2 balls, a wall, 0 balls, and then an invisible wall. So and these are going to be, each ball and each wall is going to occupy 1 spot, and my subset is going to record the positions of balls in the resulting configuration. So yeah, anyways, that is the end of the proof. If you have any questions on the proof, please let me know. Okay, thanks. Yeah, I think it's a beautiful argument, and it's actually useful quite a lot. So, and it also helps you. Yeah, let me explain some other interpretation of weak compositions, which is also, I mean, it's a popular mathematical object, which is a multiset. So multisets are just like sets, but you allow repetitions. So yeah, when you, I don't know, whatever, when you're shopping, you don't have to take objects without repetition. You can take like 2 Snickers bars or whatever, and so the result is going to be a multiset of goods you have purchased. So sometimes you want to count those as well. So a multiset. Yeah, and there it's a little bit awkward because I have to specify the goods in the supermarket. So I have to tell you what is the set you are choosing from. Multiset over S is a, well, it's not quite a set, is a collection of elements of S, but repetitions are allowed. So yeah, the idea is that repetitions are allowed, and the order doesn't matter, just like for sets. Yeah, and and the size of a multiset is the number of elements in it counted with multiplicities. Counted with multiplicities. So you got 3 oranges, that's a multiset of size 3. Yeah. So, okay, so the point I'm trying to make is that basically counting multisets is the same problem as counting weak compositions. So yeah, here's a, yeah, okay, oops. Here's the claim, which is that multisets over bracket k of size n are in bijection with weak compositions of n into k parts. So yeah, maybe, okay, how does this bijection work? What is a weak composition of n into k parts? It's a sequence A1, A2, all the way up to AK of elements which are all non-zero. So the bijection goes as follows. You take a weak composition, A1, A2, AK, and then convert it into a multiset. Right, so it's a multiset over bracket k, which means that the goods you're allowed to purchase there's k kinds of goods, like 1, 2, all the way up to k. Multiset which containing each I in bracket k exactly ai times. So for example, if I take a weak composition 2, 0, 0, 5, 1, 2, and this is A1, A2, A3, A4, A5, A6. Then I'm going to convert it into a multiset. So a multiset which contains 2 ones, no 0, no 2s, no 3s, 5 4s, 1 5, and 6 and 2 6s. And conversely, if you just record the number of 1s, 2s, and 3s, and 4s, etc., you're going to get a weak composition of n. Does it make sense? All right, cool. Yeah, and so and the corollary is that because we have this bijection, then corollary is that the number of multisets over bracket k of size. So the size is the total number of elements with multiplicities. Size n is equal to n plus k minus 1. Choose n. Yeah. And yeah, so far it's been, yeah, so far we're just getting binomial coefficients. Soon we're gonna get some more complicated numbers. But yeah, and let me also, before I get to the complicated stuff, let me mention that so there is weak compositions, but there should be also like strong compositions, right? So let me discuss just compositions, which are kind of similar. Basically, a composition is a weak composition without zero parts. So definition, a weak composition, A1, A2, all the way up to AK, is called a composition if each AI is strictly is a positive integer. So the next question is, how many compositions of n are there? How do I? Because here, right, the stars and bars argument is you're allowed to have two walls which are right next to each other, between which you're going to have zero balls. But here you're not allowed to have zero balls. So how do you count compositions? Allocate one for. Say it again. Okay, yeah, thanks. That's actually correct. So yeah, if you just take any composition and you subtract one from each of these AIs, you're going to get a weak composition, and that's kind of a bijection, right? So the claim is that the number of compositions of n into k parts is some other binomial coefficient n minus 1 choose k minus 1, as opposed to n plus k minus 1 choose n. Right. So so recall that for weak compositions, the formula was n plus k minus 1 choose n, which was the same as n plus k minus 1 choose k minus 1. So my point is that the k minus 1 part is the same, but the top part has decreased by k. Yeah. So, and the proof, as you said, is that take a composition. Yeah, anyways, I'm just going to write down the formula. So the formula is that A1, A2, all the way up to AK. If you just add 1 to each, A1 plus 1, A2 plus 1, etc., AK plus 1. So this map is a bijection between weak compositions of, I guess, n with k parts and just compositions of n with k parts. And therefore, as a corollary, we already know how many, and just compositions, yeah, one of them has to be, instead of n, I have to write n minus k, because the sum of these numbers is k less than the sum of these numbers. And so if I apply the formula for the number of compositions of n minus k with k parts, then I get exactly n minus 1 choose k minus 1. So that's the proof. Yeah. Any questions? Any questions so far? Okay. Yeah. So actually, all right. Let me ask a question, which is, so it's a slightly more complicated question. What is the number of compositions of n into an arbitrary number of parts? Okay, sum over k, 2 to the n minus 1. All right, cool. Yeah, so the answer is 2 to the n minus 1, which I guess is the sum over k of n minus of k greater than k from, I guess, 1 to n minus 1 choose k minus 1. All right, so I mean, that's correct, and yeah, thanks to those who responded, but isn't it suggestive, right? Why, if I didn't tell you how to count the ones with k parts, and you just find out that the number of all compositions is 2 to the n minus 1. So is there a bijective proof of this? So if I didn't tell you the formula, how do you prove that? How do you prove bijectively that there is a 2 to the n minus 1 options? I don't know if that question even makes sense to you, but if you just forget all I said, if I just told you a composition is just a bunch of numbers which sum up to n, why is there a power of 2 of those? Add each element to the last group or a new group. Yes, thank you. That is actually, yeah, that's correct. Right, so the idea, I guess I'm not going to be completely rigorous, but the idea is that how do you construct a composition making a binary choice at each step? So you start with a composition A1, which is just a composition of which consists of one ball, right? So you basically place one ball at one spot, and then at each step you either add a ball to your last group, or you create a new group with one ball. So maybe I add, and then I create a new group, and then I maybe create another new group, and then I maybe add a bunch. So every time I kind of make a choice of either adding a new ball to the last group or adding a new group. At each step, either increase the last a k by 1, or create a new a k plus 1, which is equal to 1. And you do this 2 to the n, and you do this n minus 1 times. So that's where the power of 2 comes from. All right. Yeah, I don't know if this was clear. If you have any questions, let me know. Yeah, I guess I have a I have some other proof in here. All right. No questions. Well, now, okay. Now, I guess, is the part where things get sort of actually complicated. At least formula-wise. Proof-wise, we're going to apply all the same kind of principles, but yeah, the next topic is set partitions, which are, and it's very easy to get confused between all these sort of, they have all similar names, but and this is why it's nice to program them or just compute a lot of examples by hand so that you get used to, you can actually distinguish them. You get it, yeah, anyways. I encourage everybody to do examples, a lot of examples by hand. So what is a set partition? So let's say you have a collection A1, A2, all the way up to AK. It's kind of like a composition or a weak composition, but it's labeled. So we say that A is a partition of bracket n into k blocks. All right, so each AI now is not a number, but it's a subset of bracket n. If the first condition is that A1, A2 up to AK are disjoint subsets of bracket n, and the second condition is that A1, the disjoint union of these sets, is equal to the whole bracket n. So yeah, and that's the definition of a set partition. And the two kind of the two basically consequences of this notation is that the order of AIs doesn't matter. And then the second condition is that the order of elements of each AI doesn't matter. Yeah. So yeah, so here I guess I have some example. Yeah, basically let me just show you how I would denote a set partition. 2, 4, 6. So that's one example of a set partition. Set partition of bracket 6 into 3 blocks. And the claim is that if I shuffle the elements inside in some way, so I'm allowed to permute 1, 3, 5 in any way I want, and then I can also, yeah, I can shuffle the sets. I can move the sets, maybe, yeah, 2, 4, but then I can shuffle 5, 1, 3. That's another way. It's the same set partition, so they're equal as sets. All right. So I should probably also, yeah, let me show you. I think I have a picture. Yeah, here's a picture from Wikipedia, which I like, and that's the. On the bottom you have a partition into 4 parts, right? These are partitions of just all partitions of bracket 4. At the bottom you have 4 parts. Here you have 3 parts, 2 parts, and here you have 1 part, which is just the whole set. And so the numbers we're going to be interested in are called the Stirling numbers of the second kind. So yeah, I want this. Basically, each Stirling number counts the the number of partitions inside of each of these slices. Stirling numbers of the second kind, which are we're gonna study the first kind a little later, but for the second kind they are denoted as of n comma k. It's just the number of the number of partitions of bracket n into k parts. So yeah, in this picture here, S4 is 1, S4 3 is what? 6, S4 2 is 7, S4 1 is 1. So, and I also, it's going to be convenient for me to allow the number of parts to be not only between 1 and n, but just to set, so there, because I'm going to study recurrences, and so sometimes for recurrences it's convenient to extend the k to run over any integer, basically. So the convention, well, I mean, it's kind of a convention, but it also completely makes sense from the definition, is that Sn0 is 0 for n bigger than 0, S0, 0 is 1, and Sn comma k is 0 when k is bigger than n. Which, if you think about it, right, the first one counts partitions of some non-zero, some positive number of elements into 0 blocks. So you can't do that. But if you have the empty set, then you can partition it into a single block. So maybe I should write it down. So this is a degenerate case where you have you partition the empty set into 0 blocks. And indeed you can do that. You can just take your partition A to be just, it has no blocks, so the union of AIs is the empty set. So it completely makes sense. And similarly, if you want the number of blocks to be, I guess each AI, I should mention that each AI has to be non-empty. Let me add this to the definition. Are disjoint and non-empty. So that's kind of the analog of not weak compositions, but the usual compositions. All right. So the question is, as usual, how do you count these objects? I wonder if, I don't think anybody can answer this right away, but if you know, let me know. Anyways, this is hard. This is hard, sort of hard. It's not a binomial coefficient, at least. So, but we're gonna give you some formula, which is not as beautiful. It's not a single kind of closed formula. It's going to be a summation. But let me show you a table of these numbers. Okay, so we have n on the left, and we have k on the top. So as I mentioned, whenever you're dealing with new objects, just make such a table using the computer, or make the first 4 rows just by hand. I already showed you in my picture that the 4th row was 1, 7, 6, 1. And then you can see that these numbers grow pretty fast. And also, our initial conditions are naturally included in this table. So you have always these ones. You have basically a triangle whose sides are all labeled by 1, and there are zeros everywhere outside of these ones. Okay, and you see that the numbers are, you see some large prime numbers, right? If you take a binomial coefficient and choose k, n factorial, k factorial, which by the way is also a powerful way to guess some formulas. You look at this formula, it has no prime multiples. Isn't the second column just 2 to the n minus 1 minus 1? Yeah, that's true. This column here is, well, that's actually part of the homework. That's one of the homework problems. But yeah, one of the homework problems asks you to compute find the formula for the first 2 columns of the table. Okay, yeah, I'm not recording the chat, so people who are not in the lecture are not going to know. Yes, but anyways, still it's a prime number, and the point of prime numbers is that you can't really. If this number were something like 6 just 2 or whatever, then you wouldn't get 31. To get 31, you need to take 31 factorial at least, or higher. So has no prime factors bigger than n. So anyways, these are more complicated numbers, especially, yeah, you're going to do this once in the homework, and you're going to see that it's slightly tricky. Yeah. So, but still you can, so instead of giving you a closed formula for just, you give me k and n, and I'm going to give you 1701, instead I'm going to give you a recurrence. I'm going to give you a recurrence which computes each number in terms of the number above it and the number above it and to the left. So the claim that I want to make is, and usually, yeah, a lot of times you can't really, or you want to find the formula, then a good idea is to prove some sort of a recurrence relation. So for each n, for each positive n and k, the formula is that S of n, the number of partitions of n into k blocks, is equal to S n minus 1, k minus 1, plus k times S n minus 1, comma k. So this is almost like Pascal triangle, except that there is an extra k. There is an extra k times this number. So maybe I should try and do some example. So yeah, the rule is that you take maybe, let's say, yeah, I guess I have to. You have to look at k. So 6 is equal to 3 times 3 plus 1 times k, or let's say k times 1. 3 plus 3 times 1. So 6 is equal to 3 plus 3 times 1. That's the, or 25 is equal to 7 plus 3 times 6. Yes, 7 plus 18 is 25. Or 65 is equal to 25 plus 4 times 10, which is also true. So that's the Stirling sort of triangle. Okay, so how do I prove such a recurrence relation? Okay. Okay. Yeah, that is correct. Thank you. Yeah. So I guess what's written here goes in the opposite direction, but basically the idea is the same, right? So you have n, s, n, comma k. Right? These are, it counts partitions of bracket n into k blocks. And so the idea is you look at the block containing n. All these blocks have to be non-empty, and exactly one of them contains the last element n. And the two cases are either maybe let's say this block is AI. Either AI is just n, or AI is n union, the joint union some bi is non-empty. Right, and so in the first case, you can remove block AI, and you get a partition of n minus 1 into k minus 1 blocks. In the second case, you can remove n from AI, and then you get a partition of bracket n minus 1 into k blocks. But the catch is that this second map is this is a k to 1 map. Right? Because if I give you a partition of n minus 1 into k blocks, then you can add n to any of the k blocks. So basically, I'm using the division principle here, and then to finish the proof, I need to add these two cases together. So I'm going to apply the addition principle. So I'm going to combine the division and the addition principle. And in general, in your problems, a lot of times you're going to have to apply these different principles together to prove some more complicated results. But yeah. I think I have 1 minute. Oh, even less. Okay. Anyways, never mind. I think that's basically a good time to stop. If you have any questions, let me know. If not, I will. Oh, okay. So there is another. Again, let me remind you, there is no live lecture on Monday. On all Mondays. So I will see you on Wednesday, and I wish you all a good weekend. Thanks.